we've been looking at acids and bases and conjugate acids and conjugate bases. And yesterday in our data booklet, we looked at understanding how strong acids to weak acids and strong bases to weak bases work. And we can see a little bit of relevance with that far right column, which is called our Ka, or our acid constant, equilibrium constants. And so strong acids completely ionize in water. They don't go backwards and forwards. You put sulfuric in water, you're going to get hydronium ions, unsulfate ions, and they're not going to come back and make sulfuric acid. Okay, they completely ionize. So all reactants get consumed and produce lots of products. So strong acids, those top 6, cannot form equilibrium. It's not a forwards and backwards piece. So if we had something in here like HCl, hydrogen and chloride, okay, so let's make this HCl and water. What we see is hydrogen ions and chloride ions. Okay? So we have complete ionization. In here, we're going to have H3O plus ions and chloride ions.
Does that say HO on the first one?
H2O and HCl.
Like the little box.
Here,
Yeah.
this is hydrogen chloride and water in this beaker. So this is hydrogen chloride, right? It's going to dissociate, and these hydrogen ions are going to reach out with water, right? And you're going to get hydronium ions. So what ionization means is that there's only going to be ions in the water. Okay? When we look at this being hydrochloric acid in water, and remembering that square brackets mean concentration. So the concentration of an acid, that's what HA stands for, H being a hydrogen, A being the acid, is going to be equal to the concentration of hydronium ions. So if I had 1 molar HCl in this beaker, I would have 1 molar hydronium ions, molar being moles per liter. Okay, they go across. So can we remember what the top 6 acids are? Not really. I'm going to start H2SO4, HCl, nitric, hydrobromic, hydroiodic, and perchloric. There's always one. I always miss one. Okay? These ones here aren't as common. These ones here I have all in concentrated form. I have in the lab. This one here, perchloric acid, because it has an additional oxygen, it's just like peroxide. Peroxide is water with 1 more hydrogen. If it gets crusty, it becomes explosive. So perchloric acid is used more in industrial settings. You don't want it just sitting around hanging out. Okay, strong bases then, they will completely dissociate. And the reason we're using the terms ionize and dissociate is typically bases are bound with a metal. Calcium hydroxide, sodium hydroxide, potassium hydroxide. They're typically bound with a metal, so they dissociate. So all reactants get consumed and produce products. They cannot form an equilibrium. A strong base. What's the charge on magnesium? Use your data book. 2 plus. What's the charge on hydroxide? 1 minus. So we got to make sure we're balancing these out. We're going to get magnesium ion, and we're going to get 2 hydroxide ions. Okay, and again, only ions exist in the beaker. Okay, only ions exist in beaker for strong bases. So what does that look like? Well, it would be the same as this. You would have a magnesium ion and you would have a hydroxide, 2 hydroxide ions. Weak acids, what? Strong bases and strong acids are not reversible. Okay? Unless you change the parameters, unless you applied heat, or unless you applied pressure, or unless you because if you change the volume, you still have the same number of ions. I think it's mainly if you just change the temperature. Okay, weak acids in water will establish equilibrium and produce small amounts of hydronium ion. Okay, so not much of a weak acid will actually separate out. So here's my beaker. And I'm going to go with hydrofluoric acid, which I find rather ironic that this is a weak acid because it does a significant amount of damage to your body. More so than sulfuric acid and nitric acid. It's the burn that keeps on burning. So let's call this hydrofluoric acid. Remember, it's indicated by aqueous. We're going to add it to water. Then we're going to get a second beaker. Well, the same beaker, but what we're going to see is, yes, we're going to see some hydrogen ions in there. And yes, we're going to see some fluorides ions in there. But we're also going to see hydrofluoric acid in there. Okay? So there's going to be some reactants. And there's going to be some products. Okay? Remaining in the beaker. When you have weak acid. So here we're going to have H3O plus, right? Because it's going to donate the proton. And we're going to have our fluoride ion. And what we're going to see is it go to equilibrium. Okay? What we can say here is that the concentration of our acid here will not be equal to the concentration of the hydronium ion over here. Because here this is all hydrofluoric acid. Over here, there's some hydrofluoric acid, there's some hydronium ion, there's some fluoride ion. Okay, so the concentrations aren't the same. Good so far? Weak bases in water will establish equilibrium and produce small amounts of hydroxide ions. It's not much of a weak base actually dissociates, not many products form. If very few products are produced with weak acids and weak bases, the equilibrium constant must be small, right? Because when we look at the equilibrium constant, it's equal to the concentration of the products raised to their coefficient over the concentration of the reactants raised to whatever coefficient they have. So if I don't have a very high number in my numerator, am I going to have a very large Kc value? No. So the equilibrium constant for weak acids and weak bases is used to determine how many hydronium ions are produced with a weak acid or how many hydroxides are produced when a weak base breaks down. And so we have this formula that we kind of look at. We look at the concentration of the acid. Actually, let's not put concentration in yet. HA is the symbol for talking about an acid, okay? Because an acid has to do what? It has to donate a proton. So HA, this is the acid, here's the hydrogen that's donating it. Plus water. If this is going to donate the hydrogen ion, we're going to see H3O plus form, and then we're going to see our ion show up. So we have some of the HA remaining as a reactant at equilibrium. But we also have some hydronium ions being produced at equilibrium. And what do we remember about pH and POH? Yeah, pH and POH. This always referred to the hydroxide ion, and this always referred to the hydronium ion. Okay? The equilibrium expression can be written for any weak acid using the acid ionization or the Ka expression. So we looked at this. This is the equilibrium expression. Okay? What do we see in the equilibrium expression? Products over reactants. So for it to be Ka, which means that we're looking at an acid expression, we're going to take the concentration of what's in our products, hydronium ion, and the concentration of our ion, and we're going to put it all over our acid concentration. This is not written anywhere on your data booklet. You need to know this. Why didn't I write water down? Because it's a liquid and these are all aqueous. Okay? So HA, aqueous, so you can only use liquids if they're all liquids, right? Plus water gives us hydronium ions and an ion. Okay, let's look at our ice tables. here we have some kind of initial concentration, right? We have to start somewhere, and these guys have no concentration. That's standard for an ice table. This is going to change by a decrease, and these will increase as it gets formed. And so at equilibrium, we'll say that HA decreases by X, and these are our X values. That part hasn't changed about ice tables. If I go through this piece here, Ka is equal to H3O plus times by A divided by HA, and I put those pieces of information in, X divided by HA concentration minus X. This should say initial here. Minus X. Okay. What did we say up here? We said that the equilibrium constant for weak acids and weak bases is used to determine how many hydronium ions. No, that's not what I was looking for. We said it somewhere. We said that they would have a very small K value. Where did we say that? Where do you see that? Yeah, I just read that. Why didn't I understand that? The equilibrium constant must be small for all weak acids and weak bases. When we see a very small Kc value or a Ka value or a Kb value, when we see a small, or this is specific to the equilibrium constant, so a small Kc value, we use that approximation rule, right? Where we multiply the concentration by 1,000, and if it's less than the concentration, we can say that what's at initial is going to be what's at equilibrium. Yeah. If this is a small Ka or Kc value, then this piece here is going to be equal to the original HA value, right? Am I making myself clear on that piece? If you have a small Kc value, then you can make that assumption that the concentration at initial is still going to be the concentration, and you're not going to see much change because it's going backwards and forwards. It's not staying all in one way. What we can say then is that Ka would be equal to X squared, if we were to summarize this, all over the concentration of HA. Well, X here, when we're talking about an acid, is our H3O plus. So the actual formula becomes Ka is equal to the concentration of the hydronium ion squared divided by your acid concentration, the initial concentration of your acid. This is critical. You have to memorize this. Stop. I don't know why it resets itself. Okay? You must memorize this. What? It would be just easier if you put it all in the book. Yes, it would be. I know. I know. Physics gets a cheat sheet. Why don't we get one? Because we're better than the physics people. That's why. Okay. Other acid-base formulas that will be used. So how do we get that hydronium ion concentration? Well, we can take 10 to the power of negative pH. That's how we get the hydronium concentration. This is review of Chem 20. This goes way back. How do we get pH? We can take the negative log of the hydronium ion. So if you need a refresher, go back through. I can give you practice. But let's look at this. Methanoic acid is present in the sting of certain ants. What is the pH of a 0.25 mole solution of methanoic acid? So it's asking us for pH. The concentration of the acid is 0.25 moles per liter. I don't have my data booklet. Alright, we're going to go here and we're going to look down the side and we're going to find methanoic acid. And we see that at the top of this page, these are all Ka constants, not Kc, Ka. We go to methanoic acid, which is right here. Formic acid, so red ants, they're the ones that sting. They've got methanoic acid in them. It has a Ka value of 1.8 times 10 to the negative 4. So Ka is equal to 1.8 times 10 to the negative 4. And it's a constant, it's unitless, this one. All right, it's asking us, what is the pH? We solve pH by taking the negative log of the hydronium ion concentration. Do we have hydronium ion concentration? No, we have HA. How do we solve this? Ka is equal to the hydronium ion concentration squared divided by the initial concentration of the weak acid. So the hydronium ion is equal to Ka times HA initial, and that's all square rooted. It'll pop back up. So hydronium ion is going to be equal to, because we have it squared here, because when we go back to our ice tables here, we have X times X, right? Hydronium ion and the acid ion, X squared in our products, and we have HA in the bottom. So X squared over HA. So hydronium ion squared, because that's what we're actually measuring. That's what we actually need. It'll click. Work through it. It'll click. What do we get for a concentration for hydronium ion? Okay. That's the concentration. Now to figure out pH. On page 8 and 9, you find methanoic acid, and it's the value on the far right. Yeah. So when I do this math, then okay. Do we remember how to do pH significant digits? To which? Yep. But do you remember how many decimals we need? Okay, in order to figure out the number of decimals in a pH, it's the number of significant figures in the problem. So this one has 2 sig digs with the 0.25 moles per liter. So we're going to take these 2 decimals. So the pH is equal to 2.17. Okay? Just as a reminder. Okay. Second problem. Propanoic acid is a weak monoprotic acid that's used to inhibit mold in bread. A student prepared a 0.1 mole per liter solution of propanoic acid and found the pH was 2.96. What is the acid ionization constant for propanoic acid? So, information that we have, the concentration of the acid is 0.10 moles per liter. The pH is 2.96, and it's asking us to find the Ka. How do we find Ka? Well, Ka is equal to H3O concentration squared divided by the initial acid concentration. I don't have H3O plus. Okay, so concentration of H3O plus is solved by going 10 to the negative pH. So the concentration of H3O plus is equal to 10 to negative 2.96. And we get what?
What? 10. So if I do 8, right?
Yeah?
You
No. Yeah.
get there.
Hang on. You've got to go 10 with the hat, negative
Why can't
2.96.
you do the E part?
I don't know why. Yeah, it's times 10 to the power of 3, not 10 to the power of a number. It's not the same thing, and I don't know how to explain it to you, but I just know it's not. So, did you see that in my calculator? You go and you hit the key where you hit the little hat button. So you would type in 10 into your calculator. You would hit the little hat symbol, which is right up on the right-hand side, and then you go negative 2.96, and then you would hit enter. And what do you get for a value? Moles per liter, right? Now I can go and I can solve for Ka. Lots of people lately have been forgetting to do these little extra pieces. Make sure that you're squaring your values. What'd you get? Okay. Well, it's a weak acid, so should my Ka be small? 1.2 times 10 to the negative 5. And there's no units, which seems weird. No half marks to be lost. Okay, and let's look at our ice tables. ICE. We're going to have some concentration of our base initially, because we got to start the reaction, which means that we don't have any values for the Hb plus ion or the hydroxide ion. This is going to decrease by some value, and these are going to go up by some value. And at equilibrium, our concentration of our B initially will be less than what the change was, and these will be X. So if I had to find my Kb expression, which was Hb plus OH negative all over B, right? That was what we said at equilibrium. Then what it looks like is I have X concentration at equilibrium. I have X concentration at equilibrium. And again, weak bases also have a low K value. So according to our whole concept of approximation rule, what we have B initially should be approximately equal to our B value at equilibrium when your K value is small. Okay? So then this here is going to be our B initial concentration. Now, X is OH negative, right? X is OH negative. It's also HB positive. It's 1x. 1x here, 1x here. So whatever we solve for x, it's going to be either or's value.
So you would just write in your
Kb. Ka is for acid. Kb, OH negative squared, divided by your initial base concentration. Okay? And this is what you have to memorize. I don't ask you for lots, but here's two that you have to memorize. All right. Now, this is where everybody trips up. pH and pOH together make the scale from 1 to 14. So 14 is equal to pOH plus pH, which means that pOH is equal to 14 minus pH. People love to forget this rule, and they just take that pH value and they stick it in the 10 to the power of negative pH, and they get the wrong value. And to your dismay, that number will be on the diploma. So remember, if you're talking base, you need POH. Your formula has no hydronium ion in it, right? It's OH negative squared. So you got to remember that piece. I can't stress that piece enough. Okay, so water can ionize and it can create an equilibrium reaction, right? H2O liquid, we get a hydrogen ion and we get an OH ion. It's what we've been talking about all along. Well, we can have a Kw, we can have a constant for water is equal to the hydrogen ion concentration multiplied by the hydroxide ion concentration. Okay? Yes, sir. Says it's on page 3. Because they changed. They did give you all the other constants. They're on page 8 and 9. Because we're better than the physics people. We don't need to have a data sheet. I don't know why. Because if you did Science 30, you would get that green data booklet and this would be there. You would have methanol, ethanol, butanol, propanol. They would all be listed for you. It's all there. It's a beautiful book.
Yeah, I love Science because all the information was
all the information was there.
That book into this cover, and then when they get in my book, we close it out.
Okay, hang on, we're not done. Hold on to that thought. Ka at 25 degrees Celsius, so room temperature, or not Ka, Kw is 1 times 10 to the negative 14. Okay? Because sometimes you got to take this number and like that value and calculate out that value so that you can move on through the rest of the problems. Yeah. You get brand new ones, yeah. I know. Okay, now there's a relationship between Ka and Kb. Ka times Kb equals Kw. Memorize this one too. I haven't asked you guys to memorize anything up to this point.
I can't remember what I did yesterday.
Well, okay, let's put all of this knowledge to good use. The characteristic bitter taste of tonic water is due to the addition of quinine, which is C20H24N2O2, a naturally occurring white crystalline compound. It's also used to treat malaria. The base equilibrium constant Kb for quinine is 3.3 times 10 to the negative 6. What is the hydroxide ion concentration of a 3.6 times 10 to the negative 2 mole per liter solution of quinine? There's a lot of words in here. Let's parse it out. It says the Kb for quinine is 3.3 times 10 to the negative 6. It's asking you for the hydroxide concentration of a base. No, it would be your base. Okay? 3.6 times 10 to the negative 2 moles per liter. Now, in order to find hydroxide concentration, this is what we know. So hydroxide concentration is going to be equal to Kb times Bi all square rooted. What? How did I get an error?
I got 3.45 times something negative.
I see what I did. Second square root, bracket, 3.3, second exponent, negative 6, 3.6, negative 2. 3 point what, Riley?
3.45.
What'd you guys get?
Did I say 3.5 or 3.4?
Me too. But what happened here?
This will be 3.4, not 3.5. So
That's fine. That's not what I'm worried about. My notes say 3.3, second exponent, negative 6, times 3.6, second exponent, negative 2. Woo! They forgot to square root this. It equals 3.4 times 10 to the negative 4 moles per liter. Okay, so teacher notes are wrong. They forgot to square root. All right, question number 2. An aqueous solution of ammonia has a pOH of 3.15. What is the concentration of the ammonia solution? pOH equals 3.15.
it's DOH and
It means that it's a base. Okay? It's asking us to find the initial concentration of ammonia. Now, we don't have enough information for anything. All we can get out of this right now is the concentration of the hydroxide ion, right? Because we're going to use this. Kb is equal to OH negative squared divided by Bi. This is what we're looking for. We can calculate this out by going concentration of OH is equal to 10 to the negative 3.15. But we still don't have this piece. How do we find Kb? This booklet only has Kas. Kw is equal to Ka times Kb. Kw we know is 1.0 times 10 to the negative 14. But what Ka do we use? Yeah, so we're going to look here and we're going to use the Ka value for NH4 plus, which is 5.6 times 10 to the negative 10. So then my Kb value is what?
What was your KA again? I was writing down 9 KW.
5.6 times 10 to the negative 10. Okay. Now that I have my KB value, I can now solve for my, well, actually, let's get an OH value here first. What's 10 to the power of negative 3.15? Okay, now I can solve for BI. So concentration of my base initial, which is of ammonia, is going to be equal to my OH negative squared divided by my KB. What do you get for a value?
0.03806.
Okay, and significant digits say what? Now we're going the opposite way. How many decimals do I have in my pH? Hang on. I don't know why my smartboard does this. Does it flicker like that in the video recording? Okay, so the number of decimals in pH equals the number of sig digs for concentration. So it's 2 decimals, so I'm going to use 2 sig digs. So 0.028 moles per liter is my concentration of my ammonium or my ammonia. Okay. All right. One more. We can do it. We got 7 minutes. We can do it. One of the uses for aniline, C6H5NH2, is the manufacture of dyes. It's also used to determine pour points. Aniline is soluble in water and acts as a weak base. When a 0.054 mole per liter solution of aniline was prepared, the pH was found to be 8.68. Calculate the base equilibrium constant for aniline. So, information first. Aniline is going to be a base. Why do you know that, Riley? Because the pH is over 7. So pH is equal to 8.68. And it's asking us to calculate KB. You have to turn pH into POH. And how do we solve POH? POH is equal to 14 minus pH. So 14 minus 8.68, 5.32. Okay, that's you have to be able to recognize those pieces. All right, it's asked me to solve for KB. KB is equal to OH negative squared divided by base initial concentration. I have base initial concentration. I'm looking for KB. So I need to get the concentration of OH ion. OH ion comes from 10 to the negative POH. POH, folks. So it's going to be 10 to the negative 5.32. So I get what for a value? 4.7863 times 10 to the negative 6 moles per liter. Okay, now I can figure out Kb. 4.786 times 10 to the negative 6 squared divided by 0.054. Don't forget to square it, which means you have to use brackets. What do we get for a value? Okay, significant digits is 2. So Kb is 4.2 times 10 to the negative 10, and there's no units. All right? Survey says that if we're doing acid-base equilibrium, that we are doing daily assignment number 7, titled Acid-base equilibrium constants and expressions. And it is 2 pages. Yep, 9 questions long. So you can do the assignment, you can do the questions, you can do the assignments and the questions. Just know that the daily assignment is due on Monday. Okay? Sure.